Okay, first things first. On the mid-year exam, question 5B, somebody sent me an anonymous feedback, which was too bad it was anonymous because I couldn't reply to that. But you can set it up so that you can get a reply from me that stays anonymous, just so you know. But somebody wrote anonymous feedback that said, hey, why did you double count points off on question 5B? I don't think that's fair. I completely agree. That was not the way we wanted to do it. Question 5 was the one on where you had to list all the asymptotic behavior, and then you had to rank them at the bottom. What I didn't want to, if you got part A wrong, but then ranked them correctly based on what you put in part A, you should have gotten full credit. Right? I mean, the only time I probably wouldn't is if you just said they were all like order 1 and then just ranked. I mean, that's ridiculous. But if you legitimately thought it was something else, then rank them appropriately. I don't want you to get double points off. So if you are in that situation, email me and I'll fix it. So no, I won't do a full regrade. I'll just fix that problem because that was something that we shouldn't have. We completely incorrectly graded, and that's that. Any other questions? Lingering questions about the mid-year exam? Nope. OK. This week in lab, we are actually going to do mid-year feedback. So it's actually something kind of unique to the CS department where we have feedback that is kind of online. Has anybody gotten an email about that yet? It might not be set up by lab tonight. Well, we'll try to figure it out. If it's set up, you'll get an email and it will say, please fill out this mid-year feedback. And then I take that and, if necessary, change the class to make it better. That's what hopefully I did last semester. But so start thinking of your constructive criticism if you have any, and try to be nice if you're being constructively critical. But I will take the comments into consideration. So anyway, we'll do that at the first 10 minutes of lab if it's working. All right, anything else before I get going? Yes, Rana. There is a pre-lab, but the feedback takes 10 minutes. Yeah, feedback takes 10 minutes, and then we're doing a lab tomorrow. And the lab is on copy constructors and assignment overload. It's a lot of stuff, but it's like stuff that you can read and go, oh, this is how it works. Anyway, OK. So 2 things we're going to do today. We're going to talk about this idea of balanced trees. And then, if we have time, which we will start on this other topic called tries, which are actually really cool. So we'll talk about that after we get done here. All right, balanced trees. So we've been talking about the idea that binary search trees could end up being degenerate, right? We can have a tree that's like 1, 2, 3, 4, 5. And there's nothing stopping us from inserting into a binary search tree such that it ends up like this, right? And that would be bad, because what is the asymptotic complexity of all our operations for this? Linear, which is not what we want. We know that binary search trees should be able to give us logarithmic behavior. Unfortunately, without some other parameters, you don't necessarily get that. So that's what we want to try to fix by having this idea of keeping a tree balanced. In other words, the right nodes, or right nodes for you guys, the right nodes should be about the same number of nodes as the left-hand side of the tree, but it's a little more subtle than that. Okay? If you had a binary search tree, can you think of a binary search tree that's completely balanced that might not give you much more benefit than linear? Can anybody think of that? A balanced tree that might be kind of not so good? Let me start like this. I'll write the same tree here, but it'll be slightly different. 10, 11, 12, 13. How could I balance that and make another part of the tree but balance it? Erica, what do you think?
If you had 9, 8, 7, 6 coming down here.
Yeah, 9, 8, 7, 6. Is that a balanced tree? Well, let's say 14. There we go, 14. Is it a balanced tree? Yeah, it's still not too much better than linear, right? Because once you go left, you got to keep going left. Once you go right, you want to keep going right. What we want is we want to make it balanced so that every node is kind of balanced. Okay? We don't want this, right? Just balancing the root is not going to necessarily help you too much, right? What we want is something like this, where we have more balanced condition, like make it so that it's more balanced, right? And such that every node is more or less balanced. Now, can you do this for every tree? Make it perfectly balanced like this? Why not? You've got to have a certain number to do it. In fact, there's an exact number that it only works to be perfectly balanced if the trees are of a certain form. Anybody want to guess what that is? How many nodes do you need to make it a perfectly balanced tree? Steve? 2 to the n minus 1, right? If there's 3 levels here, there's going to be 2 to the 3, which is 8 minus 1. 1, 2, 3, 4, 5, 6, 7. If you put an 8th one in here, right, it's going to be down somewhere down here on one of the leaves. It's not going to be perfectly balanced. So we're never going to get, well, we're rarely going to get a perfectly balanced tree, although we should strive for something relatively close to perfectly balanced. OK? You're not going to get, that should say 2 to the n. Oh, it does say 2 to the k minus 1 nodes. So there you go. Yeah, so you're not going to necessarily be able to do this. In the 50s, there were these 2 guys named Adelson Velsky and this other guy named Landis. And they came up with a binary search tree that stays, quote, balanced. And we have to define exactly what that means. A balanced AVL tree is a binary search tree, meaning it's all the nodes to the left of a node are less than all the nodes to the right of a node, right? And all the subtrees differ in height by only one amount, okay? By only one value. Okay, we've got to kind of think about what this actually means, this height. I mentioned it the other day, but let's take a look at, okay, here's our binary search tree. How did we define the height of a tree? Does anybody remember? It's a while ago. Remember how we defined the height, or the height of a node, I should say. Carly? The distance from the root is actually,
From the lowest leaf.
well, OK. So the distance from the root is the depth. Think going down, like diving into the water, the depth, how deep it is. But
The lowest leaf, like the lowest.
yeah, there you go. It's
Whatever it is.
right. It's the right. It's the amount of, it's how far you have to get to a leaf is basically what it is. So what's the height of leaves? How far do you have to go to get from a leaf to itself? 0. So we call the height of a leaf 0. So all those have a height of 0, right? What's the height of this one? 1, because it takes 1 to go to either one. OK, here's the tricky one. What's the height of the root in this case? It's actually, I heard it, it's 2 because you do the maximum, right? OK, what's the tricky little formula if you know the heights of the children to get the height of the root? Or the max plus 1, right? So the maximum of the 2 children's heights plus 1. OK, one more question. These have null nodes down here. All leaves have null nodes, right, as their children. What is the height of a null node? We're going to call it -1, right? We're going to just say it's -1, and that makes the rest of what we talk about a little bit easier. OK? So everybody gets this. You go to the maximum of the 2, and you add 1, and that gives you the height of your particular node. The height of all leaves are 0. Any null nodes are just have a height of -1. So far, so good? OK. All right. So that's what we talk about when we talk about height. Now, if we look at the following 2 trees, in fact, I'll write them both on the board here. OK, I'll write both these trees on the board here. OK, 5, and then 2, and then 1, and then 4, and 3. OK, and then 8, and then 7. OK, binary search tree? Check, right? Everybody left of 5 is less, and it works. Everything to the right is greater. OK, let's look at the height of all these different parts. OK, what's the height of all the leaves? 0. 0, 0, 0. OK, what's the height of the 4 here? 1. OK, how do you know? Because 0 and -1, the max is 0, add 1. OK, what about the height of 2? 2, the height of 8, 1, and the height of 5? 3. OK, we're good to go there. Does this meet the AVL property? The AVL property is all of every node, its children cannot differ in height by more than 1. 4, 0 and -1 by only 1. 0, 0 and 0 by no more than 1. Right? 1 and 0, that's OK. 0 and -1, that's OK. How about the root? 2 and 1, not different by more than 1. That is the invariant for this AVL tree. There's two invariants. One is just the regular binary search tree. The second invariant is you can't have your children have a difference in height of more than 1. Everybody with me? Not rocket science, right? That's just the idea. OK, let's look at the other one here. OK, unfortunately, I did all different numbers here. 7, 8, 2, 1, 4, 3, 5, and that's it, right? OK, let's label the heights for all these. All the children, or all the leaves rather. 0, 0, 0, 0. OK, how about this one? 1, 2, 3. Does this meet the AVL tree property? Why doesn't it? Which node is the one that doesn't have its children off by more than 1? Or rather does. Its children are off by 1. Yeah? It's the root, right? This child has a height of 2. This child has a height of 0. Not an AVL tree. What we need to do is turn AVL trees, if we can. If you're inserting into an AVL tree, it should already be an AVL tree. And in this case, you can't really insert one of these without already having broken the AVL tree thing. But what we're going to try to do is when we insert into an AVL tree, turn that, like if it becomes a non-AVL tree, turn it into one. That's what we're going to talk about for another few minutes here. OK? All right. Everybody get what the idea is? If you have a tree that's not AVL, try to turn it into an AVL tree. And that will retain our invariant of being this AVL quality. OK? All right. So let's see. Let me write this one on the board here. 5, 2, 8. So it's almost this. That's almost this one, right? 5, 2, 8, 7, 1, 4. Oh, this one is it. It is good. OK. When we do insert into the AVL tree, we can end up with a non-AVL tree. So for instance, where would 6 go into this tree? Yeah? No. We can insert without doing that. How would you just do a regular binary search tree insertion of 6? Yeah? Left of 7, right? You go, it's less, or it's greater than 5, but less than, and it's less than 8, so it's less than 7, so it goes right there. OK? Now it's still a binary search tree, but let's look at the heights. If you insert on the left-hand side, you don't have to worry about the heights of the right-hand side. You might have to change the root, but you don't have to worry about anything on the left-hand side. That's nice. So let's look at the heights here. OK, so we got 6, which has a height of 0, 7, 1, 8, 2, root 3. Where's the first place we go wrong? Yeah, be careful on this. It's 8, not the root. You forget that this one is what? -1. So -1 and 1 are a difference of 2. This is the problem child in this case. OK? What's wrong? What's wrong? Yeah, so this is the problem child. OK? This is the right-hand node of the right child of 8 is -1. Therefore, you get -1 and 1, and you're in trouble as far as this one. What's that?
Kind of a problem parent in this case, I guess, right?
It's the problem, right? Oh, is that what I said? Problem child? It is the problem parent. You're absolutely right. That's a good point. It is it's the problem parent. All right. So that's funny. So I sat in on or I participated in like a little faculty seminar or faculty panel the other day for possible incoming freshmen, like people who are thinking about coming to Tufts. And one of the questions the moderator asked was, what's the funniest thing that's ever happened in your classroom? And the chemical engineer guy's like, my classroom's all business. Right? And I told some story about hash tables, which we'll get to later. It might be funny. But I would have used that. The whole class I called it the problem child when it was actually problem parent. And then they would have been totally confused. But anyway. OK, so problem node in this case, right? Problem node in this case is 8. Can we rearrange this part, rearrange now, which would be back to what you originally tried to do, rearrange this so that this is now is AVL quality, or AVL matches or meets the AVL property? Can you rearrange this, just the 8, 7, and 6 somehow? How would we do it? Yeah.
Put the 7 where the 8 is.
Yeah, sure. You could put the 7 where the 8 is, and then what's going to happen?
Well, then, I mean, the root would still be fine.
Root's fine.
It would be 2 and 1. And
Forget about the left side. What about the right side?
yeah, the 7 would also be fine because now it has one child on either side. Which is the same.
So this is going to be 8 now, and this is going to be 7, 6. Yeah. OK, so now we can look at that, and we can do that, and we can say, OK, fine. 0, 0, 1. This guy's good now. And 1 and 2, still 3, but that's OK because 1 and 2 are only differ by 1. So we're good. Now, what we're going to figure out is how we make that transition and what needs to happen to make that transition. OK, that's what we're going to be doing. OK? All right. What I just did and what we just kind of figured out is this property, or is this idea called a rotation. OK, what we did when we put 6 in here, or yeah, 6 in here, I'll do it this way. When we put 8 and then 7 and then 6 in here, what we did is we said we rotated 8 to the right. What that means is 8's got to go this way. OK? And we're going to get to the details about how we do that. But what that does is we're rebalancing the tree by going to the first one that has a problem, going up from the one we inserted, going to the first one that has a problem, rotating it somehow, and that will fix our tree. Now, the problem is the details of like programming those rotations. So if you think this week's assignment has some like tricky parts with like delete and all that, or remove, right, and all that, try doing an AVL tree. Like there's corner cases everywhere, right? Now, that means that I'm not going to like make you guys do an AVL tree implementation, right? I mean, you need to understand it, and on the final, I can almost guarantee you I'll ask you to rebalance an AVL tree properly. If you looked at the mid-year from last year, about probably 60% of the students got it wrong because they tried to balance the top one, which was not the first one that had a problem. So word to the wise, study that. But we'll get there. Trust me, by the end of today, we'll all be pros at this. Okay? Anyway, we rebalance these. Okay? Now, before we get into the details of the rebalancing, here's one of the reasons it takes so much time to code. Remember how in the remove for this week's assignment, there's like 3 cases for remove? Well, for AVL trees, there's actually 4 cases for an AVL tree rebalancing. Okay? First case is the following. And they're symmetric, though, which is nice. First case is the following. An insertion into the left subtree of the left child of some node. If I was inserting, let's say I was inserting 0, it would go right here, right? And according to 2, 0 is the left child of the left subnode, which is the left subtree of the left child. The left child's 1, the left subtree would be over this way. So far, so good? We can also do an insertion into the right subtree of the left child. If I was trying to insert 1.5, it would go here, right? And 1.5, that would be the right subtree of the left child of 2, right? The other 2 cases are exactly symmetrical to that. An insertion into the left subtree of the right child. Insertion into let's see, 2.5 would be here, the left subtree of the right child. Or you could have the right subtree of the right child. What could I insert over here? How about 3.5 or something? Right? Something between 3 and 4?
Yeah, 4.5.
Oh, sorry, 4.5. You're right, 4.5. Yeah, you're absolutely right. Thank you. 3.5 would go what, here? Wait a minute. 3.5 would go here, right? This is where we want to do it. Well, it doesn't matter, here or here. Well, no, sorry, you're right. You're absolutely right. Here would be the right subtree of the right subtree of the right node. Here would still be the left subtree of the right node, of the right child. Okay. Anyway, we will do enough cases of this in the next like half an hour that we will get these nailed down. Okay, but there are 4 cases that are all symmetrical. Okay? All right. 2 of those cases, the ones that are like the same direction, left, left, or right, right, we can do what we call a single rotation. It's actually really easy. We did it right here. Okay? A single rotation is, relatively speaking, very easy. If it's a left, right, or a right, left insertion, we have to do a more complex, what we call a double rotation, but it's really just 2 rotations. Okay? It's not hard. It's just figuring out which one to do takes a little time. Trust me, I sat in my office and tried to figure this out, and it's one of those things where you forget it after a while, and you have to kind of learn it. But not hard. It's just remembering exactly what's going on. Okay? All right. Now, these diagrams tend to confuse some people. But let's try to make it so that they're not confusing. Here's what I've got up here. Okay? Circles are nodes. Triangles are subtrees. They are not nodes. They're just subtrees, right? And what that means is that they are the actual height of them, it matters, but it can be bigger than just like one node. Okay, you can kind of think of it like, in this case, you can kind of think of it as y being like a node, 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 right? Instead of like, this is like what it represents. This one represents a bigger subtree. Okay, that's all that means. What we can do, though, is we can do this rotation to make it balanced. So let's figure out if that one's not balanced right now. Okay, let's say I have k2 and k1, and then this triangle, which is pretty big, called x, and then another triangle called y, and then another triangle called z. And here's what I'm going to do. I'm just going to fix these 2 being 1 apart from each other. So let's say this one has a height of 2, and this one has a height of 1. They're just the subtrees. I could have made that 10 and 9. It doesn't really matter, right? But they're just subtrees. Height of 2 and a height of 1. This one will also be a height of 1. What's the height of k1? 3. What's the height of k2? 4. Okay. Where's our first problem node? K2 is, right? Isn't K2 the only one whose children are off by more than 1? Right? So this is an AVL tree that's got a parent that's got the root being the problem. Okay? All right. So let's try to balance this. Now that's what we're looking for, the second part. But let's just think about what we have to do here. Okay? We actually, there's a little like visualization, which is awesome. Once you figure the visualization out, you're like, oh, that's not too bad. The visualization is the following. Go to the problem node and go to the child that's got the most, like the one that's above what it needs to be. Like in this case, it's 2 and 1. So you go to this one, right? This is the problem one. You go to this one. Sorry, it's 3 and 1. That's the one I meant. So you go to the one with the 3, and you grab it. This is the visualization part. I should write a little animation for it, right? This is the visual. You grab it and you go whoosh, and you shake it out so that the rest of the tree falls underneath that one. Okay? Watch what I mean. K1, if we grabbed K1 and it becomes now the root, it basically replaces K2. Okay? All right, let's do some thinking here. For K1, what's the next biggest node to K? What's the I should say not the next biggest, but the, well, it's hard to actually say that. In K2 is the one that's going to be the right-hand child of the right child of this. Okay, I was going to say which one's the next biggest, but that's actually this one. But if you do this and you make K1 and K2 is the next biggest one, what's the next biggest one after K2? Careful. Right? It's got to be, or sorry, you're right. The next biggest one is Z. Sorry, I was thinking the next smallest one. The next biggest one is Z, so that one has to go there, right? The one that goes, Y goes between K1 and K2. Does that make sense? because y1 is definitely between them. So that means that if it's bigger than k1 but less than k2, this has to be y. So far, so good. And then x is still less than k1. And so it can be here, like this. And let's see if we've rebalanced it. What was the height of x? 2. That's not going to change. The height of y is going to be 1. The height of z is going to be 1. The height of k2? 2. And the height of the root? 3. And therefore, now we've got a situation where we've made it AVL proper. OK? I went through that pretty quick. And by the way, once you start thinking about you start writing all these heights down, you get it pretty quickly. You start getting quicker at it. OK? What's the question, Alan?
I was going to say that makes sense because you know the spot. I was wondering how you could move y to the left of k2, but you know the spot to the left of k2 is going to be free because k1 used to be there.
Yeah, that's a good point. You know that the spot next to k2 has to be free because k1 was there. Yeah, and if you went and coded this, you'd find out that that's what's nice about it is you can do these things. You go, oh, now I've just freed that one up, so this one has to go there. And I mean, there's an algorithm that does it, but we just want to see the visual part of it. OK, we get that. Hopefully, we get that now. OK, you grab the child of the problem node that's the biggest, you shake it, and then everything shakes out below, and you work out the details from there. OK? Not too bad when we do it. Turns out that, well, let's do a real one. This was the same one we did before, I believe. We added 6, right? So notice if we added 6, we grab 7, shake it, and 7, 8 over here, and 6 over there. And that's where the visualization part comes in. OK? Problem 1 was the 5, et cetera. OK? No, sorry, the problem 1 was the 8. I lied. Problem 1 was the 8. And then you shake the one below it that's the most, because this one was -1. OK? All right, so let's go on and try. Guess what? It's exactly symmetric for the other case. In this case, we want the same thing is true. K1 is the one that's not AVL anymore, because this one has, if this was 2 and this was 1, this would be 3 and 1. And so these need to change. We would rotate K1 to the left and by shaking K2, and it just works out to come out to this picture here. Okay? Completely symmetrical, which is nice when you get a left-left or a right-right insert. Works perfectly well. OK? Now, let's do this. So online, there is a nice visualization. I've showed you one of these visualizations before, but I'm going to write these down. 3, 2, 1, 4, 5, 6, 7. OK? We're going to do this. And let's see if I can find it here. Let's see. Of course I can't. Did I? Yes, there it is. Whoops. There it is. There we go. OK. So this little visualization is going to do this for us. OK. So for instance, I'm going to first add a 3. And then we're going to do it on the board as we go. I'm going to add a 3 and insert it. And the nice thing about this is that it does it on there, and we can actually follow along. So it's hard to see that, isn't it? Well, that's a 3. OK. Is this an AVL tree? Sure it is, right? It has no difference in balance, right? -1, -1, 0, we're done. OK, it's a leaf, blah, blah, blah. OK, if we want to add 2, where does it go? 1 sec, Max. Where does 2 go? What's wrong? Yeah. Sorry, don't pay no attention to that. They do it off by 1. We're off by 1 in that. Pay no attention to the heights there. Use our heights. It doesn't actually matter. It's off by 1. I don't know why they did that. It's easier. The math actually works out easier if you're doing some analysis of it with this method. But anyway, OK, where's 2 go? 2. Is it out of AVL? No. How about 1? 2 goes in there. Oop. Oh, there we go. OK. 2 goes in there. And then 1 goes. Where does 1 go? 1 goes here. Now, let's figure. This one's an easy one to tell that it's not AVL. But let's look. -1, -1. The height of 1 is 0. Height of 2, 1. Height of 3, 2. Height of the null node here, -1. It's out of alignment. which node do we grab to rearrange? 2. We grab 2 and we shake it out. And what this does is it becomes 2, 3, 1. And we are back to being AVL proper. OK? Good. So let's do it. Insert 1. And it goes in here. And it's nice here. It just goes, boop, and changes it for you. OK? All right. 4. Where's 4 going to go? Here? Is anything wrong with that AVL-wise? No, we could do it again. It's not. I mean, 0 is like 0, 1, 0. 0 and 1 are off by 1. We're OK. And 2. OK? All right. So let's insert, what did I say? 4? 4. All right. That one will go in like that. And notice it climbs back up the tree and checks it every time. Is it OK? Is it OK? Is it OK? And then it does change. OK. 5. Where's 5 go? Right here. 0. Height of this one's 1. Height of this one is 2. Height of this one is 0. Height of this one's 3. Where's the problem node? Careful. I heard some people say 2. This one's -1. I didn't write it, but you got to be careful, right? So which one do we grab? We grab the 4 and shake it out. And the 4 ends up here, right? And this one ends up being 3. And this one ends up being, did I do that? What else was on there? Sorry, 5 was on there, right? No, that's the one we just did. Right, 5. OK. Did I do that right? Yeah, 5, 4, 3, right? Yeah. OK, so we add 5 like that. And we grab the 4 and bing, like that. OK? Question, Julia? Why did we grab the 4 and shake it instead of the 3? Here's what we had, right? We had 3, 4, 5, like that. OK, if we grab the 3, well, that's not the first one that's out of order, right? If you tried to grab that, these ones, it would still probably be out of AVL tree. You do the first one that's different, like the first one that's got a child that's different. So this one was 1 and this was -1. So we say the 3 has to be the one that we, so it's the child of the 3 that we, the one with the bigger nodes, we shake the 4. OK, good. 3 does have a height of 2, but guess what? When we do watch what happens when we do the arrangement for this one first. OK, you're right. This is now out of, but this is the first one we get to. When we're going up, this is the first one we get to. When we insert it here, we go, is this one OK? Yeah, we just inserted. Is this one OK? Yep. Is this one OK? No. Let's change this one first. OK, and then when you change it, we said we got 5. We have 4. We have 4, 5, 3, 0, 0, 0, 1. Now it's 0 and 1, and we're OK. Question, John?
So if you're starting with like a balanced AVL tree, then you're inserting and you have to switch it up and shake it?
Yep.
If you're shaking on the right, as long as you just shake it once or do like the correct single double rotation, the other side of the tree will always be correct.
The other side of the tree will always be OK. If you do the root, then you've got some other, the things will change. But yeah, if you're only doing this, nothing's going to change over there.
Even if it's off like that in the beginning?
Yeah, yeah. Well, if it's off, if it's not an AVL tree from the beginning, all bets are off. But if you start with an AVL tree, do an insertion, do the rotations, you won't change the other part of the tree at all. Yeah, good question. David?
Yeah, it's actually along the same lines, but I guess I'm just going to clarify. So this is an algorithm to go from a possibly like one off from an AVL tree to an AVL tree, not to take a tree and make it an AVL tree. Right?
Yes. It's the algorithm. Oops, wrong way. It's the algorithm that goes from an AVL tree insert that could be wrong, that could not be an AVL tree anymore, back to an AVL tree. Good question. Yep, you can't do this from any tree. Now, you could probably go and turn a binary search tree by doing a whole bunch of rotations recursively, and you probably could. But we're not going to worry about that right now. OK. All right, let's see. 6 goes where? 6 goes here. Did we change anything? Let's find out. All right, 6 becomes 0. 5 becomes 1. That one's OK. 4 is now 2. Uh-oh. Right? Which one's got the problem? Is the problem? 4 is not the problem because this one's 0 and this one's 1, and 0 and 1 are OK. Right? 2 has got to be the problem one. Which one do we grab? 4. Let me draw it over here. OK, 4 is going to now become the root. OK? What is going to be the left of 4? 2 is definitely going to be the left of 4 because it's actually the next smallest, right? And then what is the, or not the next smallest, sorry, it's the, I said the same thing again. It's the one that's going to go there because it was free and it was the one we just took off. OK, what's going to go to the right of 2? The 3, because it is the only thing between 2 and it's between 2 and 4. OK, what's to the left of 2? 1. That doesn't change. OK, and then to the right of 4, what do we have left? 5 and 6. So far, so good. OK, and let's see. 0, 0, 0, 1, 1, 2. We're OK. Good? All right, one more insertion. 7. Where's 7 go? 7 goes there. And let's see. 0, 1, 2. Which one's the problem? Do we know yet? The 5 is the problem. This one's 0 and -1, and that's OK. This one is 1 and -1, and that one's the problem. Which one do we grab to shake? Grab the 6 and shake it, and you end up with 6, 5, and what was there? 7, right? OK, and let's see. Actually, I guess I'm off a bit. There's 6 going in, and 6 is the one that's going to be a big rotation. Not there. That's the problem. Boom. OK, and then 7 is going to be another little rotation between 5, 6, 7. And there it is. Good? If you want, redo this. Like, check this out online, and you can see what it looks like. OK? All right. Now, guess what? Remember I said there were 2 other cases that we had to deal with, right? Single rotation doesn't actually work for a right-left or left-right insertion. OK, why not? Let's see. OK, let's see. Let's draw this up here. K2 and Z and K1 and let's see, X and Y is a nice big one like that. OK, let's say this was 2 and 1. This would be 3. This is 1. This is 4. OK, which is our problem one here? Which one's our problem? K2 is the problem, right? Because it's the one that has the first off by 2 children. OK, so given our which one, if this is the one doing a single rotation, which one do we grab? K1. Let's see what happens. If we put K1 as the root, OK, well, that means that K2 is going to be here, and Z is going to be here. OK, and then what's going to be to the left of K2? Y. And the left of K1? X. Sorry, that's an X. Whoop, an X. OK, all right. 2, 1, 3, 1, 4. Uh-oh. Problem. Right? Right? If I could draw that little like problem guy, I would. Right? We didn't change. We didn't help the situation here. We moved the Y over, but it's still screwing up our AVL property. OK? Well, there is a solution. Do you want to think about the solution for a second? While I'm erasing this, think about what you might do to fix this. I didn't put the solution up there yet. No. It's a little tricky. The way that the tree got balanced in the left-left case was that everything was like highlighted over to the, or everything was like balanced way over to the left. Now we've got this problem where we're balanced over to the like left-right a bit. We kind of want to go that way with stuff. Okay? What we can do, and I wouldn't have like expected you to necessarily figure this out. Let's change a couple things here. Let's change the following thing, this in the following way. I'll just call this A now. Let's change X to A. I'm going to add another root here we're going to call K3. Another node here called K3. And then this is going to have a B and a C, and I'm going to call this D. Now, think about this. Have I really changed much about this tree? Right? I haven't actually changed anything officially about this. Right? This is still, we said y had a height of 2 before, right? If this was 1 and this was 1, this is going to be 2, so that's the same. This is obviously going to be the same, and everything else is going to be the same. But now, what we can do is we can say, is there a way to get this section that direction? Could we do that? Could we get this part over there by doing some rotation? Yeah. Yeah. What if we shake K3? Isn't that going to go whoop and move everything over there? Let's do it. K2 and D are going to stay the same. K2 and D are going to stay the same for right now. We're going to shake out K3, meaning this is going to become K3. OK? All right, to the left of K3 is going to be which one? K1. OK, to the left of K1, A. To the right of K1, B, because it's between K3 and K1. And then to the right of K3, C. Does this look kind of familiar? Now it looks like something we can deal with one more single rotation. Who's got the issue? Well, I don't necessarily want to draw it this way, but who would have the issue? Who could we now shake out again? K3, right? Let's shake K3 again, and it will become the root K3, right? K2 is now over here, because we're rotating this way. Right? K2 is over here. D is here. Sorry, it's getting a little in the way. I want to leave this because I'm going to use it later. D is going to be over here. Right? Let's see. Is there going to be anything to the left of K2? C, because it's between 2 and 3. OK. What's going to be to the left of K3? K1 is going to stay the same. In fact, none of this is actually going to change. It's going to be A and B. Now, I know it doesn't look right because these should be down farther. 1, 1, 1, 1, 2, 2, 3, we're good to go. Right? 2 rotations got us there. Take the node that is the problem one. OK? You go to the one that's this was the problem one. Go to if it's a left-right insertion, you've got to grab the thing on the right and shake it so that it goes to the left. Then you do the shake it again, and it moves to the right, and everything is better. Right? It's not that bad. Okay, once you actually do it a few times, and a few times is probably enough. Right? So this is exactly what we did. We remade the tree and shook it out, and then shook it again, and we are good to go. Okay. Whoop, that was sorry. There we go. OK. And then it also fixes a rotation the other direction. OK? If we insert into K2, then this is and K1 ended up being the problem. It would be a right-left, and we've got to shake twice. We've got to shake basically K2 twice. Right? Shake it once, and it goes this way. Shake it again, and it goes back over there, and everybody works out. Right? All right. Let's go back to our example again. We're going to keep inserting into this tree. We're not going to do all of them because it'll take forever, but we'll do a bunch of them until you get the point. Okay? We're going to go back to this one. This time I'm going to insert 16, 15, 14, 13, 12, 11, 10, 8, and 9. You got to be different 8, don't you? OK. All right. So we're going to insert those into this tree. OK? And I'll even do it on here for you. OK, where is 16 going to go? It's going to be the biggest in the tree, so it's got to be all the way to the right. Does this change the AVL property? No, it does not. OK, so let's do that. Put 16 in. Nothing's going to change. All right. OK, then 15. Where's 15 going to go? to left of 16. OK, now let's look at this. 0, 1, 2. But let's just stop for now, because I think we've got a problem right here. Right? A right-left insertion means we're going to have to do this twice. OK? All right? A right-left insertion is going to be, we got to do this twice. OK? So let's see. If we take, which one are we going to, if this is the problem, which one are we going to grab? 16, shake it. This is an easy one because there's nothing else there. Right? We're just going to shake 16 first. OK? And what's it going to become? 16 will, if we shake 6, sorry, are we shaking 16 here? Yeah. We are going to go, OK, if we shake 16, right, what's it going to do? Right? Actually, no, we aren't shaking. Say, hold on. We're not shaking 16. We're shaking 15. This is the one we have to do first. What's that? Watch. If we shake 15, we shake it like this. Well, it goes like, ends up being 15, 16. Can you not see it? Now we can shake, again, we now shake 15. We shake 15 twice in this case. Now if we shake 15, it will shake out so that 7 goes on the left and 16 is still on the right. So it ends up being like this. 15, 16, and what was that one? 7. OK. Why are we like, are we confused? Did I confuse you? Let's do a couple more. We'll do a couple more. Question? Yeah.
For a single rotation, you only move one down from the problem parent.
Yes.
For a double rotation, you move down twice.
You'll move down twice to the side that's the problem.
Right.
Yeah.
Follow the same insertion pattern. So if
Yeah.
we went right, in the single rotation, we follow problem right.
Yes.
For right, left, or that, yeah, right,
Yep.
left, which is what we did. We go down right, left.
Yeah, absolutely. Absolutely. OK, good. Yeah, Jade?
Sorry, how do you know if it's a single rotation help or a double rotation?
Good question. Let me go back and let's go back just one. We'll go back one step and show you here. OK, this was 7. This was 16. And we're now trying to put in 15, which was here. OK, the first one that has an issue. 0, 1, 2, but -1 and 1. 7 is the one that's the problem. OK, notice where we inserted 15. The right child's left subtree. Right child's left subtree. If it's the right child's left subtree, problem. And that's where we have to do a double rotation. How do you do the double rotation? You go down to you go to the problem, you go to that left subtree, and you grab that one, and you shake it. And that means that becomes, right, when we do that, that just switches these two to being 15 and 16. And then you shake it again, and it then changes the other direction and makes it 15, 7, 16. And now if you do the checking, you'll see that it's an AVL tree again. Let's see how the one does it up here. Up here, they actually do it in kind of one step. You can do a double rotation in one step if you remember how to do it. You just have to remember to go like left, right. It's doable. 15 goes there, right? And it's going to go boop straight to 15 and shake it like that. It's like a quick little shake in this case. OK? All right, 14. Where's 14 going to go? 14 is going to go to the right of 7. Let's look and see what happens here. OK? 14 goes to the right of 7. We've got a 0, 1, 0. This one's OK. OK. 1. What's this? Sorry. 2. 5 is 0. What's the problem now? 6 has a problem. Let's see what it is. We inserted here. We inserted in the right subtree on the left. It's way down here, but it's the left of the right subtree, isn't it? OK. So we go down 2 from this one, and we shake out 7. OK, let's shake out 7. What happens? That's going to, I'm going to erase this. So if you shake out 7, can everybody see this part of the board? Hopefully you can. OK, if you shake out 7, OK, well, let's see. I'm going to write it right here for now. 7 is going to be there. Oh, do it over up here. 7 is going to be there. OK, what's going to be to the, we're shaking it this way, so it's going that way. What's going to be just to the right of 7? 15. What's going to be to the right of 15? 16. What's going to be to the left of 7? Actually, nothing's going to be to the left of 7. But what's going to be to the left of 15? 14. We shook it that way. Yeah, question.
So there's more than one binary tree for every data set, right? For a given data.
Yes, sure.
Is there only one AVL tree?
No, there's more than, you can have more than one AVL tree, I think. Yeah, yeah, sure. Good question, but I don't think there's anything particular about an AVL tree specifically. OK, now this is going to be here. And then what's up here? We've got 6 and 5. If we go up here, 6 is still the one we worried about. We shake 7 again. And what happens? I'll do it over here. We shake 7 again. 7 is going to be like this. What is going to be to the, it's going to be rotating this way. So what's going to be directly to the left of 7? 6. What's going to be to the left of 6? 5. OK. What's going to be to the right of 7? Same thing, right? It's just going to be 15, 16, and 14. And the rest of the tree is the same, right? So that 7 replaced 6 in this case. This is going to be 4. And this is going to be 2, 1, and 3. And we're back. Now we're good again. And let's see if we're good again. 0, 0, 1, 0, 1, 2, right? And 0, 0, 1, 3, and it's 2 and 1. So we're good. We got back to where we needed to. OK, watch how it does it here. 14 goes in, goes in, goes in, goes in. And it's going to be like, uh-oh, we got to replace. Boom. OK? I know, it looks like it's a little fast on the screen. That's why I like to do it like in person for real right here. OK? All right, let's do one more. Because the next one's actually interesting. 13. Where's 13 going to go? OK. 13 goes down there. OK. 0, 1, 0, 2, 3, 1, yep, 3. And then this one is going to be 4. Where's the problem now? Yeah, this is the first one that has a difference of 2. That one's OK. This one's OK. Everybody else OK. All right. What kind of rotation do we have to do? This goes exactly back to Jade's question. What kind of rotation do we have to do here? Which one? Well, let's see. We go to the right subtree. And where do we put it? Is that the right or the left of the right subtree? To the right. So it's a right, right. So we only have to do a single rotation. Ha, let's try it. Which one do we grab if we're doing a single rotation? The 7. Let's grab the 7. 7 is going to become the root. OK. Now it gets a little tricky, but not too bad. We're rotating that way. So what's going to be to the left of 7? 4. What's going to be to the left of 4? 2. And this isn't going to change over here. OK. The fact that I'm saying this isn't going to change means that we can actually do this relatively quickly. As an aside, as it turns out, you can do a constant number of operations to get this to work. So this actually remains logarithmic, even though you first have to use logarithmic time to get to the node. It's only an added factor of a constant value. So we are still remaining logarithmic, for what it's worth, OK? Which is probably points on the test. All right. What's going to be to the right of 4? What's between, let's see, what was it, 7 and 4? The 6, right? So to the right, so it's got to be 6. And then, of course, this one's still going to be a 5. OK. And then 7, to the right of 7, the 15 and the 16 and the 14 and the 13. And if you first looked at this, you would go, there's no way that's balanced. But it is. 0, 0, 0, 0, 0, 1, 1, 2, 1, 3. We're OK. Oops, I missed one. Sorry. 2. We're actually even better. 3. There we go. OK. Let's try it. Let's see if it rotates from the, let's see, this was, we inserted 13. OK. There we go. It's got to go all the way down there. Right, right, subtree. It goes all the way up to the root and then goes boom. And there we go. OK, and that should look exactly like the one we have on here. Right? Yeah, it is. I know it seems simpler, but it goes through a whole bunch of things. David?
In practice, I know that normally we only think of the performance in terms of like the straight factor.
Yeah. Yeah.
Isn't it essentially double the amount of time it took for an operation?
Yeah.
Turn down and then back up, plus a little constant.
Sure. Doubling's fine. That's only a constant of 2.
Right.
That's still logarithmic.
Not too bad.
Right. Yeah.
There must be a balancing point at which it would be worthwhile to use this sort of tree and when it wouldn't.
Yeah, that's a good question. Asymptotically speaking, this is pretty good.
Yeah.
I mean, asymptotically speaking, let's put it this way. Somebody asked this in the earlier class. They said, wait a minute, does it matter, like, how big does a tree have to be before you start thinking it's important to use? Big, right? I mean, the first day of class, we did some, those tests. I used like 100,000 inserts and things, right? That started to make a difference. We were talking about 20 seconds versus 0.2 seconds, right? So like 100,000 starts to get up to be big, right? If we're talking about 10 or 15, no, not even going to make a difference. Your computer's like, that's like, didn't even happen to the computer, right? It's that fast. So yeah, I mean, that's a good question. But yeah, and a factor of 2 doesn't really matter in the big picture, right? Yeah, so, OK. Do I need to do any more? I don't think so. If you want, you can do some more and see what it looks like. OK, all right. This is just the algorithm I was kind of running through, right? To code up a tree, as I said, I'm not going to make you do it, but it's because it's a little tricky. But the best way to do it is recursive. It's easiest anyway. Turns out it's an easy recursive solution. It's not that fast. So if you want to do this for a library, you're not going to do the recursive one. But the idea is first insert using regular BST insertion. And then if the height of the subtree doesn't change, you're done. If you look at all the subtrees up from the root, nothing changes, you're good. If the height does change, you do an appropriate single or double rotation based on the rules we talked about. And then you can do it with 1 rotation. I watched a video from a pretty smart dude who said that 1 rotation isn't always sufficient, but I think it is. So maybe he's not as smart as I thought. But I think he is. I don't know. Here's an example code. If you want to go look at C++ code, go look at it. It might make your eyes bleed a little, but it's not bad. It's well written, and it is an AVL solution. OK? Question. Right now, we have a node having a data, a left, and a right. What else would it be really nice to have if we're doing AVL trees? The height. So you just put another variable in the class, and you call it the height, and you always update it as you enter. And then you don't have to necessarily do much work. You just have to add 1, basically. Yeah?
What does step 4 mean? Did you say do a rotation in step 3? What do you,
Step-
rotation always stuff this?
1 rotation will suffice. 1 rotation is OK. In other words, you just have to do a single or a double being 1 rotation. Like a single rotation or a double rotation, which we are calling 2 rotations just because it's like boom, boom. But remember, like it's called a double rotation. Is it really? Anybody into like espresso when they do a double shot? It's really just 1 shot, but it's like more coffee. It's like it's kind of the same idea. Like you're doing, right? I mean, they don't actually push the button twice. They push it once, and it's a bigger amount of coffee, but it's called a double shot. It's the same idea. We're just calling a double 1 rotation. Yeah, that's all. OK. All right. When Chris starts using coffee analogies, you know it's been a long day. OK. There are lots of other types of trees, right? Lots of other types of balanced trees. There's a 2-3 tree, which is kind of interesting. In fact, they want in data structure a few years ago, they made the students like implement a 2-3 tree on the midterm. Kind of tricky. They gave them like the interface and said go, and they said it was really hard. The tree that I used in the first day of class was a red-black tree. This is the one you will learn all about if you take Comp 170, which is algorithms class, and it's harder to code than the AVL tree. Slightly faster in the end, slightly fewer steps, but it's a pretty good one. And then there's some other ones there too. OK, questions on AVL trees? Any lingering questions? Think you guys got it? If I gave you a tree, you could start to keep the AVL property? I think you probably could. All right, you can practice it. Practice it. Not that bad. OK. Yeah, question, Max.
An array of numbers. How would you make an AVL tree from that?
If you had an array of numbers,
Without inserting and rotating a lot?
you would still want to insert and rotate. I mean, you just didn't. Like we said, we did 1, 2, 3, 4, 5, 6. Well, you just insert, and then it becomes balanced. And you insert the next, and you rebalance it. So you do rebalance it each time. It's a good question. probably the middle. I mean, if you can find the middle of if it's already sorted, you do the middle. Yeah, that's probably a good point. Okay, all right. So we've got a little bit of time left. We are actually slightly behind in where I wanted to be. So let's just go into the next thing, which, if there's no other questions about AVL trees, we'll go into this. One of the coolest things, this is one of the coolest data structures we see, and I think it's neat for the following reason. Have you ever been texting on your phone? Well, this is just true. Like if you have the newest like iPhone and updates and whatever, whenever you type anything, it gives you suggestions of what you want to type. And I always think that's so cool, where you start typing th and it says, do you mean the, or do you mean then, or whatever, and it gives you all these like ideas. Sometimes you actually type a letter wrong and it will autocorrect to the right thing, which is also kind of a neat thing. Does anybody ever wonder what kind of data structure you might use to like do that, to like do this like prediction of words, right? It's actually kind of a neat idea, okay, to do this. So we're going to talk about this type of tree, which has the unfortunate name of trie, right? Even though it looks like it should be pronounced tree. In fact, the guy who invented it, I think, calls it a tree. But it is a tree, but it's a prefix tree. But it's got it's dumb. But we call it a trie just to differentiate. You can call it a prefix tree if you want. But here's what it actually does. Oh, we talked about this already. AVL trees does not change the complexity of the operations. It's a constant number of operations. OK, tries. Let's say we want to search a dictionary. OK? We've already talked about doing like binary searches on dictionaries. That's all fine and good, right? But how would you represent a word in a tree? Right? Maybe a string, something like that. Would this be an appropriate binary search tree for these words? It doesn't spell like it's not a sentence or anything fun like that. It's just words I made up, right? That fit a nice category, like nice pattern here. Fire is between cow and red in the dictionary. Day is bigger than cow in the dictionary, etc. Right? This is how you might do this. Okay, typical binary tree, not so big a deal, right? The asymptotic behavior of this tree, if you're doing searching for any of this, is going to be logarithmic. If this is a balanced tree. Now, it could be a non-balanced tree in case the worst case could be order n, which would be bad. But in this case, it's logarithmic. Okay? All right. The nice thing about words is that they share these prefixes, right? Cow and corn share the first two letters, CO, right? Pit and pits share three letters. Okay? Snow and sand share one, etc. They share these prefixes. That's an interesting idea. Okay? The idea that they share these prefixes means that maybe we can do some other type of tree that takes advantage of that. Okay? Remember we did a binary tree, and we said we use a binary tree because it's nice, we can do left and right, right? We could have what we call a ternary tree, which has got 3 children per node, right? We could stick another child in here, another one in here. And that would actually get us to log base 3 behavior instead of log base 2 behavior, which actually is better, right? It means that if you had 3 nodes and you could somehow figure out the details, you would actually shorten the tree. It would not be as deep, and therefore you'd get better behavior, slightly anyway, if we could make it 3. So far, so good? OK. Right, the problem with that was that we had this like fan out issue. In other words, you'd get lots and lots of like, you can make it 3, you can make it 4, you can make it 5, whatever. There's got to be some like limit on that. You can't just make it infinite because then you don't know how to represent it and it's tough, right? But what did we just say about words that might help us a little bit? They share the characters. And how many characters do we have? 26 characters. Forget about punctuation, forget about numbers. If you want to make, you can add, but let's say that the number of total characters is like less than 100. Right? Let's just say. Uppercase, lowercase, less than 100 altogether. Maybe you make it 128 to make it nice and like computer sciencey, whatever. It might be 256, whatever. Unicode's a different story. Don't worry about that. But point is that we can, let's say we limit it to just characters, and we make it 26 characters. If we had a fan out of 26, in other words, 26 different ones, couldn't we make a different letter per child? Haha. If we make a letter per child, and there's 26 children, we can do something like the following. Okay, we can use the prefix to do something like this. Break the words up and just use their letters in each word as the key, or in other words, the child. Okay? Notice cow and corn both share the CO. So if you start here and you go, OK, I'm inserting cow, it's going to go boop, boop. And if I insert corn, it's going to go to O first because it shares the same prefix. And then it's going to have to branch out. There could be 26 different letters here, right? If we said cot, C-O-T, right, it would be a T right in the middle here, right? If we said, I don't know, collard greens or something, right? It'd be like this way, right? Whatever, you could do it. But you'd have the fan out up to 26, but that's it. Kind of nice, yeah.
Would the children have to be Booleans then?
The children have to be Booleans. The children can be characters. And in fact, we'll get into the details of this a little bit later. To compare them, you just use the character, the number associated with the character. Like there's an ASCII, called ASCII number that's associated with each character. Just need to compare those. It's not really Boolean. What we do need to know, though, is where the word ends, right? So when we get to cow, because couldn't we have cow and cows, right? Cow and cows would be, there'd be an S off here. You'd need to know that both cow and cows is a word. Okay? What I did was the following. Let's see if I can find it. Here we go. OK. There wasn't a tree, sorry, there wasn't a try built into that animation program, so I just made one. And it's kind of fun to do, right? If we have like cow, right, we get the word cow like this. What's nice about this is, well, first of all, the root is going to not be any character. Why? Because it could be 26 different characters. We're just going to make the root its own, like not anything. It's just the root. It just says everything below me is a character, etc. Okay? And then COW, we may, in this case, I'm making red mean, hey, I'm at the end of a word. Okay? What if I insert corn into here? What's it going to do? It's going to branch to the right a little bit, right? Well, actually, corn's going to go to the left, right? Because it's less than W. We're doing alphabetical order left to right. Okay? But notice corn and cow. Cow, I like that. OK, what are some other words we could enter into here? Corpse? OK, right? Notice it branched after the core, C-O-R, and then branched down here. That's cool. What else? Coward. Doesn't need to be words that like coward work. Corporation. Right? Well, it goes down the page, but right? Corporations. Let's try cows. How's that sound? Cows. Right? Cows would be right. So there's and it took me a while to get this to work so it like expands, right? Sometimes it overlaps, I think, but I'm trying to do the best I could. Anyway, cows is a word and so forth. Now, you can search for words in these, right? How easy is it to search for a word in this? Right? What do? If I search for the word, if I'm searching for the word cow, what do? Start at the root, then what? Go to the first letter. C, is it in the try? Yes. Go to that letter. Then what letter's next? O, is that in it? Yes. W, is it in it? Right? So if you go and you do search, right, C-O-W, it'll go bing, 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 and say, we found it. Right? Now, what happens if it doesn't find it? Well, let's say we wanted to search for corpser. Right? C-O-R-P-S-E-R. Well, it's just because it's going to be a fun pattern, right? Watch what happens when we search for oops, that's going to add corpser. I don't want to do that. If we want to search for corpser, right, then it'll go there and there and there and there and there, and then there's nowhere else to go, so it must not have been in the try. OK? All right, question.
What if you search for a word that is a part of another word but doesn't end?
Good question. What if we search for CO, right, or corp or whatever, right? If we search for CO, right, well, there's more letters to be found. So it gets to O and it goes, wait a minute, I've actually, it's not an end, rather. Like it's not red. Like it goes and it says, so that's a Boolean value, right? It says the end of a word is red, right? In this case, end of word, end of word, end of word. So it just checks the end of word and says, am I at the end of a word? Make sense? Yeah?
Adding on to that,
Sure. If you wanted to do that, sure. Yeah, you could do that. It would add another node per thing, but you could. Yeah, that would probably be appropriate too. I mean, you'd.
Because then for like how would be how no.
Well, it would be like COW, and then if there's no, if it doesn't, well, if you're searching for CO, right? What do you do? Like CO, you'd be done with the word. So you need to have a check here. So that might not work in that case, but you need to have a check to see that. Yeah, Cecily.
What if you tried to add?
Yeah. If you had tried to add CO, what's it going to do? There's one thing that's going to happen if we add CO. It's going to do what? No, it's going to turn red. Why? Because it's now a word we just added. Right? Yeah, good. In the back, we had a question first. Somebody back there? No? Go ahead, Ron.
Can you like put more information on the nodes that are ends of words? Be like this word is more common than this word, so it's more.
Oh, could you put more info? Sure, you could. I mean, I don't see why not. You'd be out of the realm. Yeah, that might be how you'd choose whether or not. Yeah, like corpse is not quite as prominent as corn or something, right? I was eating some corpse. I don't think you'd like that very much, right? I don't think it would. That would be the word. I was eating some CO. You don't want it to say corpse. You want it to say corn, right? But yeah, that's not a bad idea. Yeah, to have more information about it. Yeah, yeah. But do you see how this would end up being? Yeah, it got a little dark, didn't it? You can see how this is. You can see how this actually does a pretty good search, though, right? And what I'll leave you with is I want you to don't give the answer away unless you want to chat about it. But I will leave you with the question of what's the asymptotic complexity of this trie. Okay, that's what I'm going to leave you with, and then on Wednesday we'll start back with tries and do a little more details on it. Okay, questions? All right, see you guys Wednesday.